Welcome back to Calculus with Applications for our 7th week of remote learning. Before proceeding with this video, you should open the Indefinite Integrals of Basic Functions video capture sheet provided. You will be asked to complete tasks in the document throughout the video. We're still in Unit 5, where we're studying the integral. In preceding lessons, you have learned about the indefinite integral and learned to find the antiderivative of various common functions. In this lesson, we'll continue with this project and look at a few more functions and their antiderivatives. Recall from the previous lesson that if we have a function big F and the derivative of big F is little f, then big F is an antiderivative of little f. Remember that big F is an antiderivative rather than the antiderivative because there is an entire family of functions with the same derivative, different only by a vertical translation. Also recall that we introduced the notion of the indefinite integral to denote the entire family of antiderivatives, and we used the integration symbol without limits for this situation. In light of this, we have started using the instructions anti-differentiate and find the indefinite integral interchangeably. When we find an antiderivative, we add an arbitrary constant c to recognize that the indefinite integral is a family of functions. Last week we focused on finding the antiderivative of various power functions, including negative and fractional powers, and the reciprocal function, which needed special treatment. And the linear properties allowed us to deal with sums of functions and functions multiplied by a constant. This week we'll take a look at a few more basic functions from earlier in the course. We'll start with a discussion about trigonometric functions. Do you remember these derivatives? Pause the video and take the derivative of each function to see how much you recall. How did you do? Check your answers against those appearing on the slide. The following indefinite integrals follow from the derivatives on the previous slide. In a moment, you will pause to evaluate each of these indefinite integrals. For each indefinite integral, remember we seek a function whose derivative is the integrand. This gives you a way of checking your answer. As you think about each one, try taking the derivative to check if your antiderivative works. Pause the video now to try these 6 antiderivatives. Now I'll reveal the answers. Were you successful? Did you remember to add a constant c? Another thing to notice is the presence of the negative sign on the 3 antiderivatives on the right. When we take the derivative of cosine x, we obtain negative sine x rather than sine x. If we take the derivative of negative cosine x, we get just sine x as we wanted. The negative signs in the other antiderivatives show up for the same reason. These are not just results to be memorized as new formulas. Just as you store multiplication and division facts in the same area of your mind, you will also store the derivative and antiderivative rules together in your mind. Now let's try some integrals involving these trig functions. Pause the video to try each of the following problems. Let's check your work. The antiderivative of 12 is 12x, and the antiderivative of 5 sine x is negative 5 cosine x. And then we add the c. Remember that you can check this answer by taking the derivative. Similar work gives the answers to the other problems. Finally, let's recall 2 additional derivatives from earlier studies of exponential functions. Pause the video to see if you remember these 2 derivatives. How did you do? We are now prepared to consider the antiderivatives of exponential functions. Pause the video to see if you can evaluate these indefinite integrals. Did you check your answers using the derivative? The second antiderivative can be checked by seeing that the derivative of a to the x generates a factor of ln a, which then cancels out with the ln a in the denominator. Once again, these 2 basic exponential antiderivatives will serve as a toolkit as we approach more complex examples. Pause the video to try each of the following problems. Let's check your work. Let's look at one last problem that could come up when we're integrating. How might you deal with these antiderivatives? Pause the video to think about these two questions. If you thought the antiderivative of e to the 2x was e to the 2x, that's a pretty good first guess. And if you thought this might have something to do with the chain rule, that's also a good guess. You know that when we take the derivative of e to the 2x, a factor of 2 is generated. By placing a 1/2 in front of the e to the 2x, we can cancel out the 2 generated by the chain rule. Check the derivative right now if you want to see that this is true. After seeing the correct work on the problem, take a moment to try the second problem again. Did you figure out how to deal with the 12? In this case, we need to have a factor of 12 in front of the antiderivative so that it will cancel with the 1/12 that is generated by the chain rule. In these two problems, we see a very small application of the chain rule. There are many more difficult antiderivatives that incorporate the chain rule, but these go beyond the scope of this course. In this week's lesson, we have continued the discussion of antiderivatives that you started last week. You learned the antiderivative of the 6 trig functions and the antiderivative of any exponential function. We also looked at some very simple examples of how the chain rule might appear in an antiderivative. These rules, together with rules you learned last week, complete the collection of antiderivatives you will be expected to know in this course. Once again, I want to reinforce that these are not additional formulas to memorize beyond those you learned for the derivatives earlier in the course. These are simply consequences of the derivative rules. And with all the rules now in your tool belt, you have the ability to evaluate a wide variety of indefinite integrals that include combinations of these functions. In the second part of this lesson, we will consider how we might use these tools to evaluate definite integrals. We will also return to the context of particle motion to help you see how these abstract tools can be used in solving real-world problems.